Charlie, it's going to be hard for me to introduce myself at the moment.
Okay. All right, the break is not yet. All right, nothing.
In fact, there may be no break. I've got a lot of slides. So forget about morning tea.
That's why we're here.
I like to know who I'm talking to, and one of the things I need to tell you about myself is that I'm not an astronomer or an astrophysicist. I'm in fact a geologist. So I know there's one other geologist in the audience, my colleague Martin over there, Martin van Kranendonk. Are there any other geologists here?
Right.
Oh, yes, of course. Yeah, well, it's right. And depending on who I'm talking to, I also call myself occasionally a microbiologist because I've done a lot of microbiology in my time. Are there any microbiologists here? One. Okay. Still, I'll have to be careful, won't I? You're there. And I won't say I know any astronomy or astrophysics at all. Whereas if I was talking to geologists, I'd say I know a little bit of astrophysics and astronomy, a lot of which I've learned from Paul Davis, in fact.
We'll put you right as you go.
No, thank you, Paul. And I was going to say I want this to be a conversation, but Charlie's already started the conversation. You can't speak to an audience with Charlie in it without having a conversation, which I think is wonderful. I'm all for it.
Thank you.
If you need a... yeah, I'll write you a letter of recommendation anytime, Charlie. So I've decided to talk about the search for life on Mars because that's a way to get into some of the interdisciplinary aspects of astrobiology. I knew nothing about the search for life on Mars when I suddenly got an invitation in 1987 from a colleague at NASA Ames Research Center in the South Bay area of San Francisco to talk about search strategies for life on Mars. I didn't have a clue. I knew about aliens on Mars and people digging canals and all that sort of thing. I'd read the science fiction novels, but that's about all I knew about Mars. And so I said to myself, what on earth am I going to say to this expert audience of people who are actually searching for life on Mars? Fortunately, Carl Sagan wasn't in the audience at that stage. I did meet him later. And I'd had an experience as a postdoctoral student. I did my PhD in Adelaide University in South Australia, but then fortuitously and very luckily, I ended up at Yale University as a postdoc, and I had to choose a field area. And I had come across a very interesting book about Yellowstone National Park in the library at Adelaide University. So I ended up studying the hot springs of Yellowstone National Park. So I decided to think about hot springs as targets for life on Mars. And I've been thinking about that ever since. So that's where I'm coming from in this talk. I can't see you and this controller at the same time. So a little bit of context. I just want to give you some context. And you all know this. So Mercury, Venus, Earth, Mars, and so on. Not that close, of course, but that's the size scale. And there's the sun on the left. Whoops, wrong way. It's interesting. Same both ways.
So it should be just
that one.
Should be these two.
Yeah. Okay, right. So Mars there, and this is about the best image of Mars we had in the 1950s. That's all we knew. There was something icy in the North Pole. And there were vague indications of structures on the surface. That's where astronomers were in the 1950s. And there was a lot of speculation about life on Mars. In fact, there were maps of Mars where certain people had imagined when the seeing was just right that you could see all sorts of structures, including canals on Mars. So that thinking about life on Mars has a history that goes back many centuries, in fact. But this was from the late 19th century. And there were creatures on Mars, and as Mars was cooling and drying out, they were digging canals. We've already heard about aliens elsewhere in the solar system, of course. And there are people who still believe that. So again, to continue with the context, that was some of the social context. Now, the scientific context, we've seen the timescale in Stefan's talk a few minutes ago, and the Earth is 4.56 billion years old. And here's the history of the geological evidence of life on Earth. And I'm going to suggest to you that we know nothing about when life started, except that it started at least before 3.5 billion years ago, maybe before 4 billion years ago. But in fact, we've got uncertainty of several hundred millions of years, almost a billion years, as to when life actually started. And it's not clear to me what the relevance of a late heavy bombardment was, if indeed there was a late heavy bombardment. That's not clear to me either, but then I maybe have been listening to some ANU scientists too much, I don't know. Dare I say it to this audience? So we have evidence, fossil evidence of life on Earth back to around about 3.5, where it's quite convincing. I'm going to show you this in a few minutes. And all the evidence in these younger and younger rocks, this is a timescale in billions of years as a clock face. Only evidence of bacterial life, even that is controversial, though in fact there could be more complex microorganisms there, but that is yet to be determined, as I'll show you in a minute. The cyanobacteria, they used to be called blue-green algae. They're not algae, but they photosynthesize, and most of them produce oxygen. You heard about the great oxidation event in Stefan's talk. And then the macroscopic forms of life, eukaryotes are sexually reproducing organisms that have nuclei, have the DNA packaged in nuclei, which is not the situation with bacteria. And then you have the algal kingdoms, the seaweeds and so on, and you have to go right around here to younger than 1 billion years ago, and perhaps younger than 800 million years ago, to find the first invertebrates or animal forms of life. And then we occur in the last 3 minutes or less of the clock view of life on Earth. So that's the time context. We only have one sample of life, so everything we're talking about here about predicting where life might be elsewhere is based on a sample of one, which is a pretty bad start for any form of prediction.
Excuse me, when you say macroscopic eukaryotes, you're not talking about what we would call multicellular eukaryotes like ourselves, or maybe in your world of studying stromatolites, you don't make a distinction between single cell, which are mats, and you don't call that multicellular. I was wondering about that issue about the origin of multicellular. Do you place it there at the beginning of algae?
Well, of course, cyanobacteria, for example, many of them are multicellular right back here, so they're chains of cells. But no, here the word macroscopic is important. And so, and the other thing to think about in terms of the algal kingdoms, the seaweeds and so on, is cellular differentiation. So there's tissue. There's no tissue in the normal meaning of the word back here. There's no cellular, or very little cellular differentiation. There is some, but there's very little compared to the higher organisms, the eukaryotes and so on. So these are things that when you're fossilizing, you see them without the use of you see them with a naked eye. So it's size and cell differentiation that defines this group of organisms here. And then the shelly invertebrates, you've got the bivalves and the clams and things like that, and the sponges early on. And we've seen a bit of this in other versions. Here's the timescale down the bottom again in billions of years. The thing to focus on here is the GOE, the Great Oxidation Event, that Stefan's already spoken about that. And the high CO2 levels, this is what we're concerned about now, the rapidly changing CO2 level, the greenhouse effect. But there was, we presume, a strong greenhouse back in the early Archean to solve the faint early sun paradox. And there have been huge variations in surface temperature of the Earth with glaciations concentrated in several periods. This leads me to make a comment about the habitable zone. I think the standard definition of the habitable zone is very simple-minded, not to say naive. And that is, it depends on there being liquid water at the surface of a planet. Well, the fact is that the biosphere on Earth extends down to about 5 kilometres into the rock, the crust of the Earth and the rock succession. There are sufficient water and sufficient energy sources, particularly in the form of hydrogen, down to 5 kilometres or so. So the real habitable zone on Earth is not just dependent on the liquid water on the surface, unless you get into a geological tectonic argument about plate tectonics and cycling and rock alteration and so on. We really need to think about the upper part of the crust as well as the surface, and indeed the atmosphere as well as being the habitable zone. There's very much a geological approach to thinking about the habitable zone.
I can ask you about the atmosphere as well. So all the planets, rocky planets in our solar system are dominated by CO2. Not the Earth, as a lot of, or most of it is nitrogen. So what's the origin of nitrogen in the atmosphere of the Earth? Do we know it now for sure? Or is it...
Well, there's a nitrogen cycle, which is partly biological.
So it's actually biological?
Well, I don't know what proportion of it is biological, but there is a nitrogen cycle. So there are organisms that build nitrogen into proteins. For example, and there are organisms that release nitrogenous gases into the atmosphere. So there is that cycle. But
because the other thing is we've got a lot of nitrogen on Titan as well.
Yes.
Well, as far as we know, there's no biology there.
Well, we don't know, do we?
Well, as far as we know, okay. So to some extent, it's biological. We don't know exactly.
Yes.
Okay.
If you can think of any form of relatively low temperature chemistry, say below, we can say now 120 degrees, or we don't know the upper temperature limit of life. That's another thing we just don't know. But we know there are organisms that live up to 122 degrees centigrade. So think of any form of chemistry that's happening on Earth from 120 degrees down to minus 20 or so. And there are certain to be organisms there doing some of the chemistry.
So on Mars, pretty much the fact that we don't see nitrogen on Mars tells us something then about possible lack of biology there.
Well, is it true we don't see any nitrogen on Mars? I don't know. Pretty much?
Yeah.
Okay.
Wait, CO2, and then the second most common gas on Mars in that thing. Not 8%.
So what was the conclusion there? I didn't hear.
Tiny.
Tiny, well, tiny's not nothing. Anyway.
Well, when on this slide, may I ask a question also? That steam atmosphere and that you saw here, can I comment on that? Because it's kind of strange to see there. It clearly postdates the moon forming in the impact, and one can imagine it could be kind of the byproduct of a moon forming in the impact. But here it's later. So, what can you say anything about this?
Well, that's a late heavy bombardment interpretation, which might or might not be correct. And I know that you have a view on the cratering history of the moon, which is the basis for that. So it depends on what you believe about the cratering history of the moon. But that's the model on which, this is not my diagram, but that's the model on which that steam atmosphere curve is drawing. I'd like to hear about the cratering history of the moon at some stage, but I don't know whether anybody's going to talk about it. And again, we're still on context. And you've seen another version of the genomic relationships that have been discovered, particularly in the last decade, but going back to the early 50s originally. And the point I want to make here is that here are the eukaryotes, which include macroscopic forms of life. You see the macroscopic forms are only these 3 twigs here, and that's zea, which is corn, and homo, well, that's us and our relatives, and coprinus and mushrooms. So I always like to say that mushrooms are our closest relatives on the scale. And obviously, a joke that works with undergraduates normally. Didn't work here, right? Okay.
Why should that be a joke?
And the point I want to make here is that when you plot the genomic chart like this, you see there are three main domains in the tree of life. There's bacteria that we're all familiar with in one way or another. Then there's the archaea, which are similar bacteria, but chemically and genetically quite distinctive. And then there's eukarya, the sexually reproducing organisms, most of which are microscopic. So most of life on Earth, even now, is microscopic. In fact, most of the cells in your body are microbes. By far, most of the cells in your body are microbes. We're just walking culture vessels of microbes. Microbes actually run the chemistry of the Earth, at the surface part of the Earth anyway. And so, as Stefan said, when we're thinking about life elsewhere, particularly within our own solar system, we're thinking about like microbes, mostly. Unless we've read too many novels. And all of that thinking led to this famous reconstruction of what the early Earth looked like. This is from the Smithsonian Institution in Washington, and based on some work that Bill Shop's group, and including myself, did at UCLA back in the 1980s in particular. And so it was abundant volcanism. You'll hear much more about this probably from Martin, and major oceans. No continents, perhaps, most probably not at this stage. We're talking about now about the very early Earth, more than 3.5 billion years ago. And you add volcanic heat to oceans and you end up with hot springs, lots of hot springs. And the prediction was that, there would be lots of these things forming in the ocean. These are microbial reefs. They're called stromatolites. And I'm going to show you in a moment that they're still forming in places like Shark Bay in Western Australia. So this is the image that I carry around in my mind when I'm thinking about the early Earth. I can see a question coming, Charlie.
I was hoping that you could be a little bit more specific. Say earlier, you said before 3.5. You could be a little bit more specific in your mind. Is this 4 or 3.9 or plus or minus 0.2 or? I mean, because a lot of people have criticized it, says, "Oh, it was never like this." Some people say, "Oh, yes, it is." But if we could be more specific about the time, then the criticism would go away. I think. So when do you think this was?
So look, the only answer.
When was this picture taken?
Thank you very much, Paul. The only answer I can give to you is it was obviously after the moon forming event, and I understand that the best date for the moon forming event is about 4.5 billion years ago. 4.52. 4. Okay, right. 4. Right, and even that was an estimate. And 3.5, we know quite a lot about the Earth, particularly from the Pilbara and from a place called Barberton Mountain Land in South Africa. 2 places on Earth where we have really good evidence, right? That's it, Charlie.
So 3.5 to 4.5 billion years, somewhere there.
That's it, yeah. I mean, if I'm going to make one important point, it's the uncertainty in the observations based on the fact that the further you go back in time, uncertainty from a geological point of view, the further you go back in time, the fewer and fewer rocks there are to interrogate, to get evidence. And so we start using the history of bombardment on the moon and so on to try and understand what was going on. So the point that comes from all that context is that most life on Earth now is microbial, and it always has been, as far as the geological evidence is concerned. And all life on Earth requires liquid water at some stage in its life cycle. Right. So there's our model for looking for life elsewhere. So we go to Mars, and is there water on Mars? Well, we saw from that image from the 1950s that there was something icy. And that ice turns out to be carbon dioxide ice and plus water ice. And there are even ice clouds, you can see them here, in the atmosphere of Mars when the season is cold. And there's the icy pole there, and there's a lot of ice here as well. And was there ever water flowing on the surface of Mars? Yes, well, we can see these now dry river valleys, the typical sorts of river valleys. There was controversy at one stage as to whether that might have been liquid CO2, but I don't know anybody who believes that anymore. They're very much like river channels on Earth. And the scale here is that, well, that's a few hundred kilometres. And these are meteorite impact craters. We have some Year 12 students here. Who is a Year 12 student? Lots of them. I can see one hand.
Yes.
Oh, three. Good. Right. And in fact, there appear to have been massive floods at some stage. We're looking in Valles Marineris, which is the great Grand Canyon on Mars, which is about 5,000 kilometres long and up to more than 12 kilometres deep in places. And you can see traces of flow from the highlands of Mars out into the northern hemisphere of Mars. So something has flowed on the surface of Mars, and that something seems to have been water. And in fact, if you map the distribution of hydrogen in the regolith, that is the soil of Mars, using a gamma ray spectrometer in an orbiting satellite, you end up with a map like this where, on this scale, the concentration of hydrogen here interpreted as a signal of water ice in the regolith of Mars. Plenty of it in the northern hemisphere, plenty of it in the southern hemisphere, and even some in the equatorial regions. And these are the volcanoes. There's one of the volcanoes, and another one, and more volcanoes over here. So there is plenty of water on Mars, but is it flowing at the present time? Could there be life on the surface of Mars now? Well, these little channels, and the scale here is that this image is 1,500 metres wide. There are all these, well, in fact, there are thousands and thousands of these little channels that are incised in the escarpments on Mars. This is the top of an escarpment and an impact crater. Something has flowed down that escarpment, and something has come out of the subterranean environment near the top of that escarpment.
Wasn't there a paper recently saying that it was sand moving down?
Yes, there was a paper a few weeks ago saying it was not water, it was sand. But the predominant, well, we don't, that's another thing, we actually don't know. But the predominant view at the moment is that it's probably water and sand, the slurry of some sort, and something melted the subsurface ice. We know there's ice on Mars. You hit the surface of Mars with a meteorite or an asteroid, you impart a lot of energy into the system, you melt the water, and down it comes. I think that's, so Occam's razor, that's a simple.
Not to know that I think water would supply immediately.
Salty water.
Yeah, it's salty water, and it can survive long enough to do that. These are only a few hundred metres long. So it's an almost instantaneous process. Now, I don't know enough about the physics to argue about that, but it's physically feasible, so I believe.
But even in the paper that you're referring to, they had the initiation of these samples by the sublimation of water.
Yes, that's right. So there may still be, well, there is probably a liquid environment with aquifers in the subsurface of Mars now. There would be sufficient residual internal heat in Mars resulting from radiogenic decay of elements to keep water liquid, say a few hundred metres below the surface of Mars. So there could be organisms living in those aquifers just as there is on Earth. It's quite common here. And there was certainly a source of heat. This is the largest known volcano in the solar system, Olympus Mons. And that's 500 kilometres wide. 500 kilometres wide. And this caldera, the collapsed structure, and the surface is the same size as Yellowstone National Park. It's up to 90 kilometres wide. Yellowstone is also a collapsed volcano. As I say, that's the same size as Yellowstone National Park. Who's been to Yellowstone National Park? Quite a lot of people. Yeah, it's the most beautiful field area to work in on Earth, as far as I'm concerned. It's absolutely wonderful. Interesting microbiologically and chemically and in lots of other ways. And you have to avoid being eaten by the bears, which is real. Obviously, I did avoid it. So there have been about 40 attempted missions to Mars since the early 1960s. Those are missions from the Soviet Union, NASA, and the European Space Agency, and Japan, and more recently attempted by India. This is an image, well, a reconstruction of one of the rovers up there currently, Spirit or Opportunity from NASA. Very complex instruments. So we have a vast amount of information about the chemistry of the surface of Mars and the geomorphology and so on. You probably all know that this rover weighed 900 kilograms, and the process of landing it involved a sky crane lowering it to the surface. It was called the 7 Minutes of Terror. Well, the engineers at JPL in Pasadena waited to see whether it got through the atmosphere in one piece and the sky crane actually worked. Well, it obviously did work. It's an amazing feat of engineering. And it's got all sorts of sophisticated instruments on it. And so that and other rovers have shown us that there are layered sedimentary rocks there on Mars, just like the layered sedimentary rocks on the Earth. So those sorts of layered rocks have formed in water here on Earth, generally, sometimes from wind, but generally from water. And so you're sitting around in the control room at JPL, and you're deciding on the next day's a program for the rovers on Mars, and you've got to give names to the features that you're looking at. So, and what do? So you decide to call Pilbara. That sounds familiar. Wolf Creek. I watched the Wolf Creek movie last night. If you haven't watched it, don't watch it. It is horrible. I mean, as in violent and disgusting. And Hammersley, all these are Australian names. Why did they do that? Because the Pilbara in Western Australia is recognised as an analogue for many of the features that we see on Mars. So you want to interpret these features on Mars, think about the Pilbara, and I'm sure Martin will talk to you a lot more about that. Welcome to my daughter. Hello, Amanda. Sorry to embarrass you again. And so not only, though, in Western Australia do we have the Pilbara as an analogue for Mars, we have a modern example of a microbial heaven, and that is Shark Bay in Western Australia. So here we are, halfway up the coast of Western Australia, just near the Tropic of Capricorn, which is just up in here. Oh, it's just there somewhere. We're here, and the Pilbara is up there. And this area here is called Hamlin Pool. It's a very big pool. It's about 90 kilometres north-south. Very high evaporation rates in this semi-desert area. And so this is what's called hypersaline. The salinity of the water in here is up to double that of normal seawater. That keeps out most of the animals that normally graze on microbes. And so there are abundant microbes in here. And if you go to one of the beaches in Hamlin Pool, what you see is all this black material, which is a microbial mat. And you see these structures here, they're little microbial reefs, and these are things called stromatolites. It just means layered rock in Greek. Well, that's what it's derived from. That's the etymology of it anyway. And it used to be thought they were only in the intertidal zone, but in fact they're They're abundant in the subtidal zone as well. These are real reefs. So the definition of a reef is if you're in a little boat and you're motoring along and you hit one of these things, you sink. That's a reef. That was me a very long time ago. And so these subtidal microbial structures are very abundant, and they form macroscopic structures up to 3 meters high, and internally they are layered. And you'll see the relevance of that in a minute. But if you're looking for signs of life in the modern ones, that's a thumbnail there for scale. And this is the upper just 5 millimeters of the subtidal stromatolite. The white things are little sand grains, calcium carbonate sand grains, and the green are the photosynthetic cyanobacteria and other organisms, quite complex. This is a microbial mat. That is what's building the stromatolite reefs. And the main building mechanism is that during storms, all this sand is washed up onto the top of the microbial mat, needs light to grow. That's the source of energy. So these organisms either grow up or actually move up through the sand to make another layer by layer that accretes. And cyanobacteria are oxygenic photosynthesizers, and they're generally considered to be what oxygenated the atmosphere of the Earth. And here you see the oxygen bubbles in the surface of a microbial mat in Shark Bay. And so there's a big literature about when the cyanobacteria actually evolved and how that led to the oxygenation of the Earth and why did it perhaps take 1 billion years to occur. How am I going for time? I can't see.
Like 7 minutes.
Interesting. And if you look with an optical microscope at the composition of such a microbial mat, you find filamentous organisms, multicellular filamentous organisms. The length scales in these bars are 10 microns, 10 micrometers, 10 microns in all of these. So there are filaments and there are unicellular, single-celled cyanobacteria. And they're the names of the cyanobacteria and some other organisms. But in fact, they're very complex ecosystems. And if you do the genomics of a mat like that, you discover that all 3 domains of life are represented. And each one of those lines is a separate taxon, separate type of, separate species of organism within those microbial mats. So they're enormously complex ecosystems doing enormously complex chemistry, some of which results in the precipitation of calcium carbonate that turns the loose sand into rock. And some of them are methanogens, and they're releasing not only oxygen into the water and the atmosphere, but methane as well, and nitrogenous compounds.
There's one interesting point about these things, and people talk about complex multicellularity, and you said, well, this is like simple multicellularity without tissues. But sometimes we talk about an ant colony being a superorganism.
Yes.
And I'm wondering if you would call these stromatolite bacterial mats a superorganism in the sense that you probably couldn't you couldn't create a stromatolite with just one species of bacteria or another strain of bacteria, or 2 or 3, you need hundreds. And if that's the case, then they depend on each other in a way that a superorganism might do, or can you comment on that?
Yeah, no, there are in fact biofilms, which is an extremely thin version of a mat, that are almost uni-specific single species, and they occur, for example, in the hot springs in Yellowstone, where green sulfur bacteria that do anoxygenic photosynthesis, that is, they don't release oxygen, nonetheless make little stromatolitic structures. But that's unusual. So you could call these things a superorganism, but all the interrelationships are not really particularly well understood at this time. It's just so complex. This is just the bacteria, which I'm showing here. But if you look at the other domains in that same mat, this is the diversity of cyanobacteria in that same subtidal stromatolite mat. And this is the diversity of the archaea in that subtidal mat. And so unraveling all of that complexity is going to take lots of PhD students and lots of time.
But a single strain mat is the exception rather than the rule.
Yes, very much so. So if we go to the Pilbara, and now we're 3/4 of the way up Western Australia and in this area here, and for those of you who know the geography, Port Hedland is just in there. And there's the time scale, the length scale there, it's 100 kilometres. And this is an old diagram, but 20 years ago, each of these stars represented a known locality for the discovery of fossils of some sort, mostly stromatolites. Quite a few of them, as you can see. Martin is responsible for a lot of the mapping of this area now, and there are beautiful detailed maps, but that's another story, and I'm sure he'll tell you. And that's what the Pilbara looks like, and at the top of these hills here are layers of sedimentary rock that are relatively thin. Most of the rock is lava flows of various sorts, with cross-cutting what are called dikes, that are the underground plumbing structures associated with hot springs that were on the seafloor or lake floor 3.49 billion years ago. And Martin, this is Martin's diagram. I didn't talk about it later, but you can map out in detail the dikes themselves. And when you get near what was the seafloor or lake floor at the time, there are these domal structures which can be compared to the structures in Shark Bay and interpreted as probable stromatolites. And some of them have conical layers. This is a natural outcrop section, so which is perpendicular to the layers. And there's and the conical structure is particularly interesting. I'll tell you why in a moment. And so if you were to reconstruct what the crust of the Earth looked like at that time, you'd have a lake or a sea inlet into a caldera with circulating very hot waters and hot springs on the floor of that body of water. And some of those hot springs would have been like the so-called black smokers that are seen in many places on the modern seafloor, with forms of life in them, temperatures of up to 122 degrees centigrade. But mostly the environment was more like this, and this is White Island in New Zealand in the Bay of Plenty. And that island is about 5 kilometres wide at its greatest dimension. And this is a collapse structure on the top of White Island. It's an active volcano. I've had PhD students working on the microbiology of this environment, and the field trips to the middle of that volcano last about 1 or 2 hours. People have died in there. No, the people who've died are not PhD students. They were people mining sulfur. There are native sulfur in there, as you'll see in a moment. And if you land on the shore of that volcano, there's no sign of life there at all. And first looking at it, there's the shoreline, there's the black volcanic sand, and there are some PhD students. And still no sign of life apart from the PhD students. Yes.
Just 2 minutes.
2 minutes, oh, right. Yeah, there's a special definition of a minute here. But if you look very closely, and there's a pen for scale, you see this little rivulet of hot water, very hot water, that's, well, up to 50 degrees centigrade here. Yellow sulfur, native sulfur is called, and all this black stuff and brown is iron oxidizing bacteria. And the green stuff there are in fact algae. But algae that can live up to about 50 degrees centigrade. But if you go to Yellowstone, my favourite place, and this is not showing up very well, but in some of the springs in Yellowstone, there are microbial mats that form little cones that are very similar to the conical stromatolites that we see in places in the Pilbara. And there's Martin demonstrating some of these in the field, and I'm going to go on fairly quickly here. And there's a vertical natural cross-section through a conical stromatolite. And this little things up here typical stromatolites. They're called the Mickey Mouse ears, generally by geologists here. And the layers that form by some periodic process, such as we see in Shark Bay. But not only are there, they're 3.49, but that one, the last one was 3.4 billion years old approximately, and formed on a continental shelf, such as the continental shelf off Sydney on the east coast of Australia. And that's a succession of views. I'm going to run through this very quickly now. And if you were to reconstruct what these things looked like when they were forming, they were little cones on the seafloor, little rocket nose cones. And there they are in the field. That's a 10 centimetre scale. There you see the cones. And we think we know how those cones form. And in the modern world, they're built by filamentous bacteria, or cyanobacteria that are moving up towards the light and accreting structures as they move towards the light. So we have evidence for what's called phototaxis, the movement in relation to the light. And if you wanted to, you can use it as an argument for there being cyanobacteria all the way back to 3.4 billion years ago, or maybe even 3.5. It's very contentious though. And we don't have to rely just on the shape of the sediments. There are, in fact, cellularly preserved cells and microfossils. Here seen in thin slices of silica rock, looked at with an optical microscope. There's the scale 10 micrometers.
Can you just tell us how quickly they grow? This structure?
Nobody knows how quickly they grow. We're probably talking about hundreds of years for the structures that are shown. And the ones in Shark Bay, the big ones, are no older than 5,000 years, and they're still forming. So they've made it to 3 meters or so in 5,000 years, but they're still pretty slow. And where the growth rate, the accretion rate in Shark Bay has been measured, it's of the order of 1 millimetre a year. They form, they get eroded in cyclones, they form again, but on average, they grow about 1 millimetre a year. But we don't know in the case of the fossil ones. There's no way with those fossils of resolving the timescale. There's no dating technique. So there are all sorts of, I'm going to skip this, all sorts of microfossils there. And if we really wanted definitive evidence as to what the organisms were, it would be good to have some of the distinctive biochemicals that are found in the nucleus of organisms or in the cell walls or whatever. And those chemicals can be preserved. They're called oil. Hydrocarbons, once they've been dehydrogenated to some extent. And they can be found in rocks. And if you can prove that they were actually original and not the result of later migration of oil through the rocks, which also happens, very complex field of study, then you have molecular fossils as well as microfossils and as well as stromatolites. But the oldest of those known at the present time are about 2.7 billion years old. There is organic matter in the older rocks. There is interesting evidence that there might be biomarkers, as they're called, in some of those other rocks. But I'll let Martin talk about that. I'm sure he'll mention that. And so to analyse those things, you use gas chromatography, mass spectrometry. Skip that. So, an assumption that's made when people find stromatolites in the rock record is that they were built by cyanobacteria. That assumption can be wrong. As I was saying before, there are modern examples of microbial mats and biofilms that don't involve cyanobacteria. So this is what we know about the biological history of the Earth. Nothing. At 4 billion years ago. There is extremely contentious evidence from Labrador. It's nonsense in my view. And there is problematic evidence at 3.8 billion years ago in Greenland. But once we get to 3.4 and 3.5 billion years ago, we have diverse lines of evidence from the Pilbara and from Barberton Mountain Land in South Africa for a number of different sorts of organisms. And we're getting into younger and younger rocks, so we have more and more rocks to interrogate to get evidence. And so we put a lot of rocks at about 3 billion years ago with diverse life evidenced. And by the time we get to 2.8 to 2.7 billion years, we have very abundant evidence of life, almost certainly including cyanobacteria. And that's about when the great oxidation event is recorded chemically in the rocks of the Earth. So the way I like to summarise it is the Pilbara has the oldest convincing evidence of life on Earth. That's at 3.49 billion years ago. That's convincing is the key word there. That's not to say there isn't interesting, contentious evidence back to 3.8 to 3.9. And if we're going to look for life on Mars, I think we should be going to ancient hot spring systems. We should be looking for an ancient Yellowstone on Mars. And there are strong indications of such a place already, and I'm sure Martin will talk about that. And there are interesting recent publications by PhD students and Martin himself, including this student Tara Docking, published just a few months ago. And I'll leave it there. Thank you.